All right, Chapter 9, we are going to be testing claims. We're going to be looking at another type of inference. We looked at confidence intervals in Chapter 8. This time we're going to be looking at things called significance tests. And I'll be taking each one of these sections and splitting it into two videos for each one. So we're going to talk about the basics today. The next section we get into population proportions and then population means. I hope you're seeing a similarity between the last several chapters. We introduce the topic, we look at proportions, we look at means. It's all related. We're going to use a lot of the same skills that we saw in the last few chapters also. So, in the first section here, you should be able to talk about hypotheses for a significant test. You should be able to interpret p-values. And in the second video, we'll look at type 1 and type 2 errors and describe the relationship between significance level and power. So I want you to read this introduction, pause the video, and take a moment to read this. So the type of inference that we're using is a significance test. And what we're doing is we're assessing evidence, that is data, about some claim and deciding whether or not that claim is maybe true. Our significance test is a formal procedure for comparing observed data with a claim. And that claim we call a hypothesis. And we're assessing the truth of that hypothesis. What we're looking at is how to make these claims, how to write these hypotheses, the logic that goes behind them, and the statistics that go behind checking if there's truth to the claims being made. So these tests are going to be asking if the statistical data, if the sample data is giving good evidence against a claim. So if we took lots of random samples and the claim were true, basically what's the probability that we would get the result like this? And we've been doing this. We've looked at several simulations throughout this course, and we've been deciding whether or not a claim has been true or not based on sort of, well, it sort of seems like it might be false or wrong, or it sort of seems like it's true. We're going to give a more formal approach to this today. So, let's introduce it. We have a basketball player claiming to be an 80% free throw shooter. To test this claim, we have him attempt 53 free throws. He makes 32 of them, which makes his sample proportion, his p-hat, equal to 0.64. What can we conclude about his claim? It's definitely lower than 80%, but is this data different enough to reject his claim? We can use software to simulate this, assuming that he is an 80% shooter. So here's the M&M's, the Reese's Pieces simulator that we looked at a couple chapters ago with sampling distributions. The probability of an orange, that's going to be the probability that he makes the free throw. Number of candies, that's the number of shots he takes. The number of samples is going to be 400. I'm going to watch him shoot 53 throws 400 times and look at the distribution. So there's our distribution. And what we see is that his claim of 80% is over here, but what he actually did is down here. And we could do this over and over again, and we'll get a distribution that looks pretty much the same every single time. And what we're looking at is, in the long run, how much evidence is there that he's shooting 80%? Well, if he shot 60%, 64%, in 400 trials, there were only 3 times where that happened. So the observed statistic, our p-hat, is so unlikely, 3 out of 400, that the actual parameter value probably isn't true. We probably should reject that claim that he shoots 80%. But just because we're claiming that the player's claim is incorrect, based on our evidence, there's two possible reasons for why he might have only made 64%. The first reason would be that the player's claim is correct, but he had very bad luck, and a very unlikely outcome occurred. Or the population proportion is actually less than 80%. He's a liar. So the sample result is not unlikely. The true proportion is wrong. The basic idea is that an outcome that would rarely happen if a claim were true is good evidence that the claim is not true. Doesn't guarantee it, though. Now let's talk about stating hypotheses, because part of this formal process is being able to write down the hypothesis for what's going on. We're going to make two statements, two hypotheses. The first claim is called the null hypothesis. Usually the null hypothesis is what's being claimed. It's something that is of no difference. It's the claim we hope or suspect to be true. Or the claim that we hope or suspect to be true is oftentimes called the alternate hypothesis or alternative hypothesis. So here's the definition worded another way. Let's look at an example. Let's go back to this basketball player to illustrate what's going on. In our free throw shooter example, our hypotheses are P equals 0.8 is the null hypothesis. H sub 0, that's the notation we use. H sub 0 is P, the population proportion, equals 0.8. The alternate hypothesis is that the true proportion is less than 80%. That's what we're wondering. Is that claim true? That's our alternate. In any significance test, the null hypothesis will have this form. H sub 0 colon parameter equals value. The alternate or alternative hypothesis will have one of these forms. HA colon parameter is less than a value or greater than a value, or parameter is not equal to the value. To determine the correct form of the alternative hypothesis, you must read carefully the problem. The alternative hypothesis is called one-sided if it looks like these first two. If we're only worried about being less than or greater than the value. It's two-sided if it's stating that the parameter is different from the null hypothesis value. It could be larger or smaller. That's going to be the third one. So these first two are one-sided alternative hypotheses. The third one is a two-sided alternate hypothesis. One thing to remember, ladies and gentlemen, is hypotheses always refer to the population and not to a sample. When stating the null and alternative hypotheses, you must talk in terms of parameters. You cannot talk about p hat and x bar. It must be p and mu. So, job satisfaction. Read this problem, and then I want you to attempt to answer part A and part B. So go ahead and pause the video right now and try and answer these two things. All right, so what's going on here? The parameter of interest is the mean, mu, of the differences in job satisfaction scores. The appropriate hypotheses would be the null hypothesis is mu equals 0. The initial question asks whether job satisfaction differs, and the alternative hypothesis is two-sided. So we're going to say the null hypothesis is 0. So we're wondering, is there no difference between these? That's our null. Our alternative hypothesis is there a difference? Is one better than the other? So mu does not equal 0. The null hypothesis states the claim that we are seeking evidence against. the probability that measures the strength of the evidence against the null is called a p-value. So here is the formal definition for a p-value. It's a probability, ladies and gentlemen, and the smaller the p-value, the stronger the evidence against the null hypothesis provided by the data. Small p-values are evidence against the null because they say the observed result is unlikely to occur when the null is true. Large p-values fail to give convincing evidence against the null because they say the observed result is likely to occur by chance when h sub 0 is true. So, here's our job satisfaction study and our two hypotheses. We have data, we have x bar, we have the standard deviation, and we find that on average, what this means is that x bar tells us on average 17 points higher. Researchers performed a significance test. We don't know what a significance test is yet, but they did this and they found p was 0.2302. What does it mean for the null hypothesis to be true here? Well, it means in this setting, the null hypothesis means the difference in satisfaction scores for the entire population is 0. That is, if H0 is true, if the null hypothesis is true, then the workers don't favor one work environment over the other, on average. Pause the video and try to interpret the p-value. All right, so the p-value is the probability of observing a sample result as extreme or more extreme in the direction specified by the alternative hypothesis, just by chance when H0 is true. Because our alternative hypothesis is two-sided, the p-value is the probability of getting a value of x bar as far from 0 in either direction as the observed x bar when H0 is true. That is, on average, the difference of 17 or more points between the two work environments would happen 23% of the time just by chance in samples of 18. So let's process this again. So an average distance difference of 17 or more, x bar being 17, will happen 23% of the time just by chance in samples of 18, if the true population mean is 0. That's the important thing to take from this. There's a lot of words, a lot of talking here, but the meaning behind the alternative hypothesis and the p-value is this last sentence. And so an outcome that would occur so often just by chance, that is roughly 1 in every 4 random samples, when H0 is true, is not convincing evidence against the null. We failed to reject the null hypothesis, mu equals 0. So this probability, this 0.23, tells us that 17 can happen by chance. 17 isn't unlikely enough to reject the null hypothesis, so we fail to reject it. And a note to make is that that doesn't mean that the null hypothesis is true. So the final step is to make one of two decisions: reject the null hypothesis or fail to reject the null hypothesis. If our sample result is too unlikely to have happened by chance, assuming the null is true, we'll reject the null hypothesis. Otherwise, we fail to reject the null. And again, a fail to reject the null does not mean the null hypothesis is true. You should never, ever use the words except h sub 0, or use any sort of language implying that you believe the null hypothesis is true. In a nutshell, our conclusion in a significance test comes down to this. There's no rule for how small p should be in order to reject the null hypothesis. It's a matter of judgment and depends on specific circumstances. But we can compare the p-value with a fixed value that we regard as decisive, that is significant. We're going to call this the significance level. We call it alpha, the Greek letter alpha. When our p-value is less than the chosen alpha, we say the result is statistically significant. If the p-value, so the definition, if p is smaller than alpha, we say the data are statistically significant at level alpha, and in that case we reject the null hypothesis and conclude that there is convincing evidence in favor of the alternative hypothesis. So we can modify that flowchart from just a second ago to this. So let's look at two examples here. Then we're done for today. We go on to the next thing. We make this more formalized. So, batteries. We have a null hypothesis that the average length is 30 hours and an alternative hypothesis that the average is more than 30 hours. Mu is the true lifetime of these new fancy batteries. Our P is 0.0276. Somebody did this test and found that P was 0.0276. What conclusion can we make for significance level alpha equals 0.05 and 0.01? Well, since the p-value is less than alpha, the result is statistically significant at the 5% level. We have sufficient evidence to reject the null hypothesis and conclude the company's deluxe AAA batteries last longer than 30 hours on average. If our significance level is alpha equals 0.01, 1% significance level, our p-value is greater than that, and we don't have enough evidence to reject H sub 0. Therefore, we cannot conclude that the AAA batteries last longer than 30 hours. So that's where we will stop. My strong suggestion is watch this video again. Focus on the meanings of these examples. Now that you've seen where we're going with it, watching it again might fill in some of those blanks. Have a wonderful day, and I'll see you in part 2.